Hi, in this video, we are going to continue on Unit 6 periodic table, and this video is going to be the last video of this entire unit. And in today's video, we are going to have two focuses. First of all, we are going to finish off talking about the group 0 nonmetals, and after that, we are going to introduce something called ions. Now, ions are a type of particles in which its formation is closely related to the group 0 nonmetals. So that's why we put them together. Now let's get started. So group 0 nonmetals, again, if you go back to the periodic table, we are referring to these members, starting from helium, goes down to neon, argon, and then all the way to radon. Alright? So these groups are called group 0, not the group 8. And these on the far right hand side on the periodic table are obviously the nonmetals. Now, similarly, it has its common name and it is called the noble gases. Now, it is called noble gases because you know, nobles in the past, they are the higher class, the upper class, they don't have to work and they can enjoy their life. So nobles, you can think about it as the people who don't have to work and they are kind of lazy. So noble is actually referring to the fact that they are very unreactive. Okay? Now, let's look into these members of noble gases. Now, let's skip helium at the moment and let's focus on neon, argon, and krypton. Alright? Now, again, you will be able to see the similarity in terms of the electronic arrangement. You see that all of these noble gases are having 8 electrons in their outermost shell. So they have very similar electronic arrangement, and because of that, they are referred to as group 0. Now remember, it's not group 8, even though it has 8 electrons in the outermost shell. They are called group 0. Now, having these electronic arrangement, we say that these electronic arrangements are referred to as the octet structures. The octet structures. Now, what do you mean by octet structure? Now, octet, OCT, actually refers to 8. Like octopus have 8 legs, right? So oct means 8. Now, octet structure means a particular electronic arrangement where there are 8 electrons in the outermost shell. Now, please remember this, because this is very important. And why is it very important? Is because whenever you have an octet structure, you are very, very stable. Okay? Whenever you have an element having 8 electrons in the outermost shell, they are very, very stable. Now, if they are very stable, that means they don't want to change. If they don't want to change, that means they are unreactive. So that's why you can tell why group 0 nonmetals are unreactive, because they all have octet electronic arrangements. Okay? Now, but what about helium? Now you see helium, it doesn't have 8 electrons in the outermost shell. As a matter of fact, that it only has 2 electrons, right? So it can never get 8 electrons in the outermost shell. However, it is still classified as group 0. The reason is because for helium, there is a special structure exclusively for helium, and some atoms that is having just a few electrons, such as hydrogen, such as lithium, such as beryllium, so on and so forth. But here, if you want to focus on helium, there's a special structure exclusively for helium, which is called the doublet structure. A doublet structure. So a doublet structure, basically, dub means 2. It's like double, right? So doublet structure basically means 2 electrons in the outermost shell. Okay? However, this one is only exclusively for helium as an element. Alright? Now, why does it have to do with the exclusiveness only for helium? Because some elements such as, for example, calcium, which is number 20, isn't it? So if you work out the electronic arrangement, it is 2H2, right? Now you notice it also has 2 electrons in the outermost shell. However, do you think that calcium has a doublet structure? Of course not, because calcium, as you can tell from the previous video, calcium is very reactive, right? It reacts with water quite vigorously. So obviously calcium is not noble, it's not unreactive, right? It's very reactive. Plus the fact that, well, gas, right? So it kind of tells you that all of these members are gaseous state in room temperature. Calcium is obviously a solid, all right? So here, doublet structure, bear in mind, 2 electrons in the outermost shell, but exclusively for helium, okay? Now down here, you see, noble gases are having either a doublet structure or an octet structure, which is very stable. Okay, very stable. So that's why noble gases are chemically inert. Okay, inert basically means unreactive. All right. So in DSE syllabus, you can basically assume that all noble gases have no reaction at all. All right, no reaction at all. Now, I also want to talk about the application, because these noble gases being so stable will have their application. For example, for helium, now helium is referred to as the most stable element on the periodic table. It is used as the filling gas in balloon or airship, like those Zeppelin, right? The reason why helium is chosen is because it is less dense than air. Now, of course, you have to be less dense than air so that you can lift up an airship. But you may say, what about hydrogen? Hydrogen is the lightest and therefore the less dense, the most less dense element on the periodic table. Why don't we choose hydrogen? Well, in fact, hydrogen was used long time ago, like in Germany, where they built the German Zeppelin, those airships. They used hydrogen to fill up those airships. However, hydrogen being so flammable and explosive, and any sparks or any fire occurring in the airship will be able to burn the whole airship down in just less than a minute. So, and it did happen before, and obviously it led to a very tragic accident. So, therefore, hydrogen is not chosen to fill up balloons or airship, and helium is chosen as a much safer substitute as the hydrogen in these applications. Okay, so less dense than air, and it is not explosive or flammable. Alright, now neon has its application using for neon lamp or neon signs. Okay, of course we are talking about the filling gas in the neon lamp or neon signs. Okay, now here for argon, it can also be used as a filling gas in light bulb, especially those incandescent light bulb, like the tungsten light bulb, because you know the tungsten wire inside the tungsten light bulb is actually heat up to over 3000 degrees Celsius, and only at that temperature the tungsten element start to glow and give out the white light. But thinking about if the metal is heated to like 3000 degrees Celsius, and if the light bulb inside is holding air, then obviously some combustion or some reaction will take place between the tungsten metal and any gases in the air. Even nitrogen could be reacting with the tungsten at such a high temperature. That's why argon is chosen to fill the light bulb of a tungsten light bulb. So this is to prevent any reaction or burning of the tungsten filament. Okay. So now that would be all the application. Down here for the physical property, very simple. They are gas, they are colorless, and they are insoluble in water. Chemical properties, like I said in DSE syllabus, they do not react at all, so there are no reaction, okay, involving in group 0 nonmetals. Now, even though the reactivity increased down the group, it doesn't react at all. Okay. All right. So that's it for the group 0 nonmetals. All right. So just now we say that noble gases are very stable because they have the octet structure or the doublet structure. Now, in other words, if an atom or a chemical species, if they do not have an octet structure or a doublet structure, then we can say that they are actually unstable. We can say that those species are actually reactive. Okay? Now, in chemistry, everything tries to do their best to become stable. Everything tries to achieve an electronic arrangement such that they are stable. So, in other words, all the atoms except the noble gases, they try their best to get an octet structure or a doublet structure so that at the end of the day, they become very stable. But the question is, how can they achieve the octet structure or the doublet structure? Now, okay, so here page 44, in fact, we try to go to the back of the note where you look for an empty space and we try to jot down something. So here you can put down, refer to page 44. Okay. Now, let's just say we have a sodium atom, okay? A sodium atom, number 11, and the electronic arrangement will be 281, no doubt, okay? Now, all of you should know that sodium is a highly reactive metal, right? We have learned the chemistry about the group 1 metal. They react vigorously with water. So, they are unstable, they are reactive, simply because they don't have an octet structure. So if you study its electronic arrangement, you see the problem appears on this outermost shell because it has this one electron there. Now the question is, how can it convert itself into one of those octet structures where we can find it, the group 0 element? So actually, it can do so by two methods, theoretically. So it can either lose electron, because if there is an electron here, it can remove one outermost shell electron. Okay? Right? So if you remove one outermost shell electron, then it becomes 2,8, isn't it? Okay? Now, it can also choose to gain altogether 7 electrons. When they gain 7 electrons, then the sodium will become 288, isn't it? So, no matter this or this will be very stable because both of these are octet structures. Okay? Now, let's think about their subatomic particles. So, for example, if you go back to sodium here, you know that for sodium, it has 11 protons and 11 electrons. So, altogether, it has 0 charge, isn't it? Because it is balanced. But right now, if you try to follow these two, after removing one outermost shell electron, if you look at sodium here, it is still having 11 proton, but now it only contains 10 electron, isn't it? So if you look into the charges, we have 11 positive and 10 negative, so it should have positive 1 charge, isn't it? That extra proton results in a positive 1 charge. Okay? So what about sodium here? If it gains 7 electrons, then now the proton number doesn't change, but after gaining 7 electrons, now it becomes 18 electron, isn't it? So if you look into the overall charges, then it is negative 7 charge, isn't it? So my question is, are they still atoms? No, because remember, for atoms, they must be electrically neutral. That means they don't have any net charges. But here, it has a positive 1 charge, it has a -7 charge. So they are no longer atoms. Now they become something called ions. They become something called ions. So here we call this one actually sodium ion. Now leave some space here. Sodium ion. Okay? And this one is also sodium ion. Leave some space here. Okay? Now, because they are ions, they have charge, we want to distinguish them between the atoms. So we want to indicate the charge. So to indicate the charge, we will put the charge on the top right hand corner. In this case, we have a positive 1, so we put down just positive here. Positive. Okay? Because positive 1 and 1 is redundant, we don't have to include that. Okay? And here, because it's -7, so we will put down 7 negative. Now it is the rule. It has to be like 7 negative, like 2 negative, 3 negative. We can't say -3, -2, -7. It has to be 7 negative. Okay? Now, so after including the charge, so now you look at the entire ion as a whole. Okay? So this one is a positive ion. Now for positive ion, we call them cation. Cation. So you get CAT here. So altogether cation. And here, this is anion. Okay? So a cation is positive and anion is negative. Okay? Whenever you have a positive ion, we call them cation. Okay? Or you can say positive ion. Here, if it is an ion having negative charge, we call them anion. Okay, anion. Okay? Now, so this is how a sodium atom can form an ion. However, think about it. So there are two possible ways, but which way is a better choice? So if you are a sodium atom, will you prefer removing just 1 electrons, or do you prefer gaining 7 electrons? Of course, the first method is easier. So in fact, in reality, sodium will only go for this method, and it will never go for this method. Okay? Simply because it is too much work. It takes too much work to gain 7 electrons, so it is impossible to gain 7 electrons, plus the fact that having 7 electrons, look at the subatomic composition, like you need to have 11 protons controlling 18 electrons, so it is quite unstable. Like we have so much electrons, so many electrons, they are out of control. So that's why it is seldom reaching such a high charge for ions. Usually for ions, they reach at most 3 positive or 3 negative. Okay, so that's the idea. That's why sodium is reactive, because sodium has this one extra outermost shell electron, so it is quite easy to lose that electron to become a very stable sodium cation. And in other words, sodium is very eager, very willing to lose that electron, because simply by losing that electron, it can become very stable. So that's why it really wants to become sodium ion, and therefore sodium is very reactive. Okay? Now let's look at another example. We have chlorine. Okay, so chlorine atom. So this is number 17, 287. Okay, again, chlorine is unstable because it doesn't have the octet structure or the doublet structure. So again, you get to choose 2 ways to become stable. You can either remove 7 outermost shell electron, which is quite difficult, or it can simply gain 1 electron. Okay, so I think now you get the gist of it. If you want to become a very stable ion, so you will actually Right? So of course, if you are a chlorine atom, you want to become stable, you want to get an octet structure, you will definitely go for this method, and you don't go for this method, isn't it? So that's why for chlorine atom, it will choose to gain an extra electron to become this one, the chloride ion. Now bear in mind the name of the ions. This one is not chlorine ion, it's not chlorine anion, we call them chloride anion. Chloride anion. Okay? We have the IDE suffix. Okay? And this one you can put down as chloride cation, but this one never exists because it never undergoes step. Okay, so we are focusing on this one and this one. Okay, so now you understand how an atom forms an ion. They form an ion by either gaining or losing electrons, and as to how many electrons it has to gain, how many electrons it has to lose, it depends on their electronic arrangement. So at the end of the day, they try to attain an octet structure or a doublet structure. Okay? Positive ions are called the cation, negative ions are called the anion, and you need to indicate a charge by putting the charge on the top right-hand corner. Remember, if you have one positive, one negative, you can simply put down positive, negative. The one is redundant, you don't have to include that. And if you have multiple charges like positive 2, positive 3, you don't put down positive 2, you put down 2 positive. You don't put down negative 2, you put down 2 negative. So these are the rules. Okay? Now, let's go back to page 44, and we quickly fill in the blanks and highlight keywords. Okay, so formation of cation. Remember, cation are the positive ions. Okay? Now, first of all, ions are charged particles. Charged particles. Very important. Now, cation, they are having the positive charges. Okay? And we know that metal atoms from group 1, group 2, group 3, they are unstable because they have extra electrons in their outermost shell. So they tend to lose electrons to attain an octet or doublet structure. Okay? And a metal atom, now bear in mind those terms. An atom becomes a positively charged cation after losing electrons. Okay, very, very important. Metal atom becomes a positively charged cation after losing electrons, and it depends on which group you are. If you are group 1, you lose 1 electrons. If you're group 2, you lose 2 electrons. If you're group 3, you lose 3 electrons. Okay. Now this is using the electronic diagram to show you the formation of ions. Now you notice after losing electrons, there are 2 shells left with electrons. And here, you want to indicate a charge, you use a middle bracket and you put the charge on the top right hand corner. And you notice the electronic arrangement of this sodium ion is actually the same as a neon atom. So that's why it is very stable. Okay? So here, after losing 1 electron, sodium ions attain the same electronic arrangement as neon atom. Therefore, it is very stable. Okay? Now this is using an equation to show you how the sodium atom becomes sodium ion. It loses 1 electron and the electron exists as a product. Okay? Now, down here, formation of anion. So anions, first of all, they are negatively charged. Okay? So this time, it is the non-metal atoms that have a high tendency to form anions. So non-metal atoms from group 5, 6, 7, they are unstable. So they tend to gain electrons to attain an octet electronic arrangement. Gain electron. So now the non-metal atoms become a negatively charged anion after gaining electrons. Okay? Again, atoms becomes ion. Atom become ion. Okay? Now, looking at the electronic diagram. So chlorine atom, when it gains an electron, it becomes a chloride ion. So bear in mind the suffix here. There's a change in the suffix. Now you notice we will usually use another symbol to represent that extra electron which is not originated from the atom. So originally we use crosses, and now that extra electrons we use a dot to represent. Okay? After gaining that electron, remember again use a middle bracket to enclose the electron diagram and put the charge on the top right hand corner. Okay? Now this chloride ion happens to have the same electronic arrangement as argon atom, and therefore both are very stable. Okay? So you see after gaining one electron, chloride ion attains the same electronic arrangements as an argon atom. Therefore it is very stable. Okay? In terms of the equation, you see the chlorine atom gains an electron to form a chloride ion. Okay? Now down here, this is also very important. Elements of the same group, they tend to gain or lose the same number of electrons to attain octet or doublet structure. What does it mean by that? That means here, for example, sodium is group 1 metal, it loses 1 electrons to become sodium ion. What about potassium? Same, potassium loses 1 outermost shell electron to form potassium ion, having positive 1 charge. Similarly, for the next member, okay, like cesium, okay, they are doing the same thing because they all have the same number of outermost shell electrons. Same idea goes for group 7, right? All the group 7 elements, they will gain 1 electrons to form ions with 1 negative charge. This is the idea. Okay? So now on the right hand side here, we have some practice question. Again, we are going to draw some electronic arrangement, but this time they are talking about the ions. Now, first of all, we want to put down electronic arrangement, and then electron diagram, and also name. So we have 3 tasks for each species. Okay, so let me do one for you. So the first one here, ions of magnesium. Now, first of all, you need to know magnesium. Let's do some rough work outside the box. Magnesium, Mg, is number 12, isn't it? So originally it is 2H2. Okay? Now it is going to form an ion. So it is going to have an octet structure. So does it prefer losing electron or gaining electron? Now of course it will prefer losing electrons because only losing electrons so that it can become octet structure. Also, magnesium is a metal. Metal loses electrons. Okay? So how many electrons does it lose? Well, probably 2 electrons because it's group 2. So now it becomes Mg 2,8, right? And then having 2 electrons. Okay? And now it bears a 2 plus charge because losing 2 electrons makes it having 2 plus charge. If you forget why it is 2 plus charge, again you can check. 12 proton, 10 electron, so altogether positive charge. Positive 2 charge, isn't it? Okay? 12 proton is because the atomic number is 12, 10 electrons is because it has lost 2 electrons, so only 10 left. Okay? So right now, let's put down the electronic arrangement of ions of magnesium. So it is 2,8. Okay? Electron diagram. So we have Mg. So now it's 2,8. So actually the electron diagram is quite similar to what we did before. Okay? But we don't stop it here because we also need to include a middle bracket, and then you put down 2 plus. Okay? The name is magnesium ion. Magnesium ion, or you can put down magnesium cation. Okay? So this is how you do it. Let me do one more example. Let me do oxygen here, ions of oxygen. So ions of oxygen here, again, we can do this rough work. So oxygen is number 8, so it's 2,6. Okay? Now, does it gain or lose electron? Of course, it will gain electron. So it will gain 2 electrons to become oxide ion, O2 minus. And then this time it is 2,8, okay, which is very stable. Alright? So electronic arrangement based on this one. So O, 1, 2, cross, 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 dot, dot. We try to use a different symbol to represent the electrons that is not originated from the atom, it's coming from somewhere else. Okay? Also, middle bracket, and then you put 2 negative. Okay? And lastly, the name. So, do we put down oxygen ion? No. Now for non-metals, when they form ions, the suffix will be changed. Will be changed to IDE. IDE. So this one is actually oxide ion. Oxide ion. Okay? So all the negative ions will be ending up with IDE. Okay? So this is the idea. Now, I would like you to spend some time try to do the rest of the 6 questions. You may not sure about the name, you can leave it there and I will check the answers with you. So now pause the video and attempt these questions. Alright, just quickly check the answers. Okay, so these are all the answers. Now, of course, in the real exam, you don't have to do all this rough work, but this is to show you how I think throughout the deduction of the electronic arrangement of these ions. Okay? Now, before I end today's video, I want to ask you, can you tell me which chemical species are having the same electronic arrangement? Okay, which chemical species are having the same electronic arrangement? Now you realize that actually these 4 chemical species are having the same electronic arrangement. And these 3 are having the same electronic arrangement as well. And beryllium ion is having a doublet structure. So you realize that different ions, even though they are coming from different elements, they may end up having the same electronic arrangement. So that's it for this video.